Welcome to lecture 3 of single factor experiment. In this lecture, we shall be dealing with the test on individual treatment means. In a fixed effect model, suppose the null hypothesis H0 is rejected, we conclude that there are differences between the treatment means. The question naturally arises as to which treatment means differ. To answer this question, comparison between treatment means has to be made. Such comparisons are usually made by conducting the following tests. 1. Test prior to experimentation, and 2. Test after experimentation. Test prior to experimentation. This test makes use of what we call contrast. By contrast, we mean any linear combination of treatment totals with the restriction that the sum of coefficients is 0. That is, linear combination of the form C equal to sum j from 1 to k of Cj y dot j, where Cj is the contrast coefficient of treatment j and y dot j is treatment j total, such that the sum of the coefficient is equal to 0. Any linear combination satisfying this condition is what we call a contrast. Choosing contrast coefficient. Suppose there are 3 treatments and we wish to test the following hypothesis. H0 tau 1 is equal to tau 3 against the alternative that tau 1 is not equal to tau 3. To construct a contrast, all we need to do is to move tau 3 to the left so that the null hypothesis is restated as tau 1 minus tau 3 equal to 0. This then suggests the contrast of the form C equals to y dot 1 minus y dot 3. That is treatment 1 total minus treatment 3 total. Clearly, as you can see, the coefficient of the treatment totals here are C1 equals to 1, that's the coefficient of treatment 1. C2 is equal to 0, coefficient of treatment 2, since there is no treatment 2 present here in the contrast. And C3 equals to minus 1, coefficient of treatment 3 total. As you can see, the sum of the coefficient here is equal to 0. Let us look at another hypothesis. If we wish to test this hypothesis, H0 tau 3 is equal to tau 1 plus tau 2 all over 2. This null hypothesis can be restated as half tau 1 plus half tau 2 minus tau 3 equal to 0, which suggests the contrast in the form C equals to half of y dot 1 plus half y dot 2 minus y dot 3. And here again, the contrast coefficients are C1 half, C2 half, and C3 minus 1. Clearly, the sum of the contrast coefficient is equal to 0. Note that contrast coefficient must be chosen prior to experimentation. Why? The reason is that if coefficients are selected after experimentation, most experimenters would construct tests that correspond to large observed difference in means. These large differences could be due to presence of real effect or due to random error. Sum of squares of contrast. The sum of squares of any contrast is defined as sum of squares of contrast C is equal to C squared all over sum as j goes from 1 to k of nj Cj squared, where nj is the number of observations under treatment j and Cj is the contrast coefficient of treatment J. We note here that the sum of squares of contrast has a single degree of freedom. To test our contrast, we make use of a statistic defined as F naught equal to sum of squares of contrast C all over mean square for error. And this statistic has approximately F distribution with one numerator degrees of freedom and n minus k denominator degrees of freedom. The orthogonal contrast. Two contrasts with coefficient Cj and Dj are said to be orthogonal if sum of Cj Dj as j goes from 1 to k is equal to 0 for a balanced design, and it is sum as j goes from 1 to k of nj Cj Dj equal to 0 for unbalanced design. Note, for k treatment, a set of k minus 1 orthogonal contrast will partition treatment sum of squares into k minus 1 independent single degrees of freedom component. Example 1. The response time in milliseconds was determined for 3 types of circuit used in an automatic value shut-off mechanism. The results were as shown in the table below. Here are the 3 circuit types T1, T2 and T3, and these are the response time. A. Let us test the null hypothesis that tau 1 is equal to tau 2 is equal to tau 3 is equal to 0 against the alternative that they are not all equal to 0. B. Construct a set of orthogonal contrast, assuming that at the outset of the experiment you suspect that the response time of circuit type 2 to be different from the other two. Use alpha equals to 0.05. Solution. A. The ANOVA table for the test is as given below. Please note that this ANOVA table has been obtained in our previous example. Here we have source of variation between treatment, error, and then total. The second column is for degrees of freedom. We are comparing 3 treatments, so the degrees of freedom for treatment will be 3 minus 1, which is equal to 2. There are altogether 15 observations, so the total degrees of freedom is 15 minus 1, which is 14. Then the error degrees of freedom is 14 minus 2, which is equal to 12. These are the sum of squares. For treatment it is 543.6, for error is 202.8, and for total is 746.4. And these are the mean square, which is obtained by dividing the sum of squares by the degrees of freedom. So for treatment, 543.6 divided by 2 will give us 271.8. For error, 202.8 divided by 12 is 16.9. Then the F statistic is obtained by dividing the mean square for treatment by mean square for error, and that will give us 16.1. Clearly, using alpha equal to 0.05, you see that this test is significant at that alpha level, because from the F table, the value of the F statistics calculated here, which is 16.1, is greater than the table value. Hence, the test is significant. That means the H naught is rejected, meaning that the treatment effects are not all equal to 0. So we therefore conclude that the response time for the three circuit types actually differ. B. We were to test the hypothesis that the treatment 2 effect and the other two are actually different. So first, let us consider the null hypothesis that tau 2 is equal to tau 1. From here, we construct a contrast which is equal to C equal to y dot 1 minus y dot 2. We also consider the test tau 3 equals to tau 1 plus tau 2 all over 2, which suggests the contrast of the form D equals to y dot 1 plus y dot 2 minus 2y dot 3. Please recall we were asked to construct a set of orthogonal contrasts. So looking at these two contrasts, C and D, you see that these two contrasts are orthogonal because the product of their coefficient is equal to 0. Here we have 1 times 1 plus minus 1 times 1 plus 0 times minus 2. You observe that the sum of this contrast coefficient is equal to 0. Hence, the two contrasts C and D are orthogonal. Now let us compute the actual value of our contrast and their respective sum of squares. Here are the observations under treatment 1, that's circuit type 1, and the total observation there is 54, that's y dot 1. The total observation under circuit type 2, y dot 2 is 111, and y dot 3 is 42. So we therefore compute our contrast C as y dot 1 minus y dot 2, which is equal to 54 minus 111, and that will give us minus 57. We also compute contrast D as y dot 1 plus y dot 2 minus 2y dot 3, which is equal to 54 plus 111 minus 84, and that will give us 81. Now let us compute the sum of squares of each of these contrasts. For contrast C, the sum of squares is equal to C squared all over sum, as j goes from 1 to 3, because k is 3 in this case, of nj cj squared. Here nj, that is n1 is 5, n2 is 5, and n3 is 5. That is the number of observations under each circuit type. C1 is 1, that's the contrast coefficient of y dot 1 is 1, C2 is minus 1, and C3 is 0. So that will give us this sum to be equal to 10. So therefore sum of squares of contrast C is minus 57 squared all over 10, and that will give us 324.9. Similarly, we compute the sum of squares of contrast D as follows: D squared all over sum, as j goes from 1 to 3, of nj dj squared. Again, n1 is 5, n2 is 5, and n3 is 5. Then d1 is coefficient of y dot 1, which is 1, d2 is 1, and d3 is minus 2. So putting them into here, that will give us the sum to be equal to 30. So the sum of squares of contrast D is 81 squared all over 30, and that will give us 218.7. We are now ready to construct our ANOVA table by inserting the row for contrast C and another row for contrast D in the previous ANOVA table. Here, the degree of freedom for contrast C is 1. Degree of freedom for contrast D is also 1. Then the sum of squares for contrast C is 324.9. For contrast D is 21.7. Then the mean square, we divide the sum of squares by the degrees of freedom, will give us 324.9 for C and 318.7 for D. Then the F value is obtained by dividing the mean square for contrast C and D respectively by the mean square for error, and that will give us 19.2 for contrast C and 12.9 for contrast D. So we note that, as stated earlier, that the sum of squares of treatment is equal to the sum of squares of contrast C plus sum of squares of contrast D. That is 324.9 plus 218.7 will give us 543.6, and also the sum of the degree of freedom of these two contrasts is equal to the degree of freedom of treatment. That's 1 plus 1 will give us these two. Conclusion. In our first hypothesis, where we were required to test the hypothesis that the three treatment effect, that's the three circuit type, are all equal to 0, against the alternative that they are not all equal to 0, and we were to use alpha equals to 0.05. As you can see, the calculated F value is greater than the F value at this level. Hence, we reject the null hypothesis and then conclude that the response time for the three circuit types differ. In the second hypothesis, we were to test the hypothesis that the effect of circuit type 1 and type 2 are equal, against the alternative that they are not equal. Again, you can see that this test is significant at alpha equals to 0.05, because the calculated F value is greater than the table value. Hence, again, we reject the null hypothesis and conclude that the response time for circuit type 1 and 2 differ. And lastly, we were to test the hypothesis that the effect of circuit type 3 is the average effect of circuit type 1 and type 2, against the alternative that they are not equal. Again, at alpha equals to 0.05 level, the test is significant. We therefore reject H0 and conclude that the response time for the circuit type 3 and average response time for circuit types 1 and 2 differ. Thank you for watching. Keep on watching. You will be happy you did.